Hello and welcome to part 7 of Dev Maths and Stats Refresher course, lecture 8, where we finish off this demonstration. Done the first couple of parts. Just want to know how covariance of x and z compares to the original covariances, varx, var, or the original variances and covariance when you change these variables. And you get some nice rules out of this. So we're looking for the rest of these rules. This one, by the way, we already had covariance of x and x. I think I showed you that. If you put 0 there, so z is basically x, it's the same thing, then covariance of x and x is the same as variance of z and variance of x. So we've got that rule already. So this is just variance of x. So the covariance of a variable with itself is just its variance. Then we want to get covariance of x, y. It's useful to be able to simplify this kind of thing. So what you need to do there is to make this one and this one. So z is now x plus y. So covariance of x with z is the same as covariance of x with x plus y. So this is cov x with x plus y. So where does this come from? Well, we've just seen that covariance of x and x is something to do with variance of x. We've also got variance of x and y. So what you can try is adding this to this. Yeah, you get this. So your rule is that this is equal to, it's almost like multiplying out. It's covariance of x with x, which gives you var x. It's almost kind of distributive. Plus covariance of x with y. Okay, so that's kind of intuitive, that one. Next one is covariance of x with a multiple of y. Okay, so these two, this is a special case of this one, so let's do that. So we do minus 1. So cleared that one. So now z only depends on y, sorry. So pardon me though. So z you can now see is minus y, and the covariance of x with minus y, if you compare that with that, it's minus the covariance of x and y. So it's just been multiplied by minus 1. And if you check a few other things by putting 2 here, so y is now, x is now 2y, so the covariance of x with 2y is twice. Just multiply that by 2, obviously. If you put 10, it might be clearer. So it just multiplies by that factor. And so on. So that'll multiply by 4. So the rule here is that this is just A times the covariance. So if you multiply one of the variables by a fixed number, that just multiplies the covariance by that number. Which is sensible, but it's actually not very useful. We've kind of already got this, covariance of x with a plus b, because you see it's just distributed, so it's covariance of x a plus the covariance of x with b. Similar to this one up here, except it's instead of x you've got a different one. So covariance of x with a and covariance of x with b. And then these ones we need to add the correlation coefficient for. So the final part, put in a formula that gets you a correlation coefficient in a single cell between x and z. So down here would be good, maybe just underneath this. Let's put the correlation coefficient down here. X the definition of this is basically just the covariance, but it's adjusted by dividing by the spread of x as measured by the variance, and multiplied by also dividing by the square root of the square root of this and the square root of this. So the standard deviation is x and the standard deviation is z. So it's SQR square root them both of this times this. So there's your correlation coefficient, and the difference is this is always going to come out between -1 and +1. And it's also got some really nice properties, which we'll show you now, that improve on some of the other things. So, okay, we need to complete some of these rules. Where's the rules? What's the correlation coefficient of x and x? Okay, this should be fairly obvious. So if I set A1 and B0, that means that basically x and z are the same thing. So x and z are exactly the same thing. Correlation coefficient is 1. So it's perfectly correlated. But you can't tell from covariance. All you can tell from covariance is a big positive number, so they're highly correlated. But you can't tell how well. This tells you it's perfect, because in actual fact x and z are the same thing here. So correlation coefficient of x and x is 1, precisely. That's a simple answer. And then here we can just experiment with this. This basically means x and then any combination of a linear combination of y. So you can experiment with various things. So in other words, get rid of that, put that back in. So this is x and y. So that's the correlation coefficient between x and y we just had. But now you start looking at these, take y and transform y. So multiply y by a number, double it, and you see that that doubles the covariance thing. But what does it do to the correlation coefficient? Nothing at all. Stays the same. If you multiply it by 10, nothing happens. So it's invariance to linear, so multiplying by positive numbers and to add things on. So if you add some numbers on, like add 50, nothing. Take off 100, not a sausage. It doesn't change the underlying correlation. Because if you think about it, that's really brilliant, because it means that it doesn't matter what units you're measuring things in. It doesn't matter if there's a fixed offset. The underlying correlation is not affected by things like where you're starting from to measure from, or the units you're measuring in. So none of that affects it. But of course, flipping to a minus does, but just perfectly inverts it, because you go from a positive correlation to a negative correlation, because you're measuring one of them backwards. But changes the scale, even changes the scale of that, don't affect it. So the rule here is that it equals to, see, this is what I mean about drawing a convincing row, it's hard. So when A is greater than 0 or negative row of x So this should be xy. Making sense? So for positive A, anything you throw at it has no effect at all on the correlation coefficient if A is positive. Similarly, if it's negative, it has no effect, just flips it to negative, but otherwise doesn't affect it. So correlation coefficient is a really good measure of how two variables may be varying together, which is independent of scale and starting position of measurement, as it should be. Okay, so I think that's the end of that demonstration. Great, so we've filled all the roles in the spreadsheet. Always happy with rules. So in the next video, we'll just go on to look at some examples to finish off the lecture. But for now, thank you for watching.